Okay, we've got a uniform rod, mass m, length 2a, and it's resting in equilibrium. A smoothed peg, which therefore can only offer reactive force, no friction, and a rough ground. We've got the angle theta, and we're asked in part A to show that S is equal to 2/5 mg. Okay, let me add the extra forces to the diagram, and we'll work on from there. Okay, there we are. I've got the mass of the rod at a distance of A away from point A. We've got a smooth peg offering this reactive force S, perpendicular to the rod, friction and reaction from point A. And in part A, we've asked to show that S is equal to 2/5 mg. This is a moments question, and the best point to take moments is around the point A, which means we can ignore, for the moment, the reactive force and the friction force associated with that point. And all we've got is mg, which we're going to have to turn through an angle of theta. There being a theta in here, and there is the triangle that we can be used to substitute for cos theta or sine theta as required. Okay, moments. And we'll do them clockwise from A. The clockwise force is mg, but we have to turn it through cos theta, and it's a distance of A away from the point A. So I've got mg cos theta multiplied by A, and that, because there's no other forces, must be equal to the force S, which is already perpendicular, so we don't have to turn it at all, but we have to multiply it by 1.5A. Straight away, the A's cancel. So substituting a value of 3/5 for cos theta, I get that mg multiplied by 3/5 is equal to S multiplied by, well, 1.5 is 3/2. The 3's cancel, and therefore I can say that S is equal to 2/5 mg, which is what they asked us to prove. Okay, part B, we're now given that the coefficient of friction between the rod and the ground is mu, and the rod is in limiting equilibrium. Find the value of mu. Well, in these moment questions, there is nothing to stop you going right back and resolving the forces vertically and horizontally to solve such a problem. There's no acceleration in any direction, so the balance of forces, once you've turned them all vertically or horizontally, the forces will balance. So let's have a go at that. Okay, resolve vertically. Pointing directly upwards, RA plus S, and we have to turn that through a value of theta, so we multiply it by cos theta. And that is equal to the only force going downwards, mg. We know S and we know cos theta, so let's put those in. So I get RA plus S, which is 2/5 mg, and cos theta 3/5 is equal to mg. Pushing this around, therefore RA is equal to mg minus, this is 6, this is 25, 6/25 mg, which is equal to 19/25 mg. So now I'm going to resolve horizontally, and I'm going to take to the right as positive. The force very much to the right is F. The force to the left will be the resolution of this force, the S force, turned through an angle of 90 minus theta. So this is S sine theta. And those are the only two forces. I can say they must be equal because we are in equilibrium. So this is S sine theta. And as we are in equilibrium, F is equal to mu R. So this is mu RA is equal to S, and I might as well put the sine theta in. Sine theta will be the opposite over the hypotenuse. So this is 4/5. We need to make mu the subject, so therefore mu equals S, which is 2/5 mg, multiplied by 4/5. Now divided by RA, so we can turn this guy upside down, so this is multiplied by 25/19, and I've got 1/mg. The mg's cancel, 5 times 5 is 25, and that cancels with the 25 on the top. And we're left with 8 on the top over 19. And that's the value of mu. And that's the end of the question.